Okay, now consider how do we use Henderson-Hasselbalch equation. Okay, the first example is this: sodium hypochlorite. Okay, was dissolved in a solution proposed to pH 6.20. Question is find the ratio of hypochlorite and hypochlorous acid in the solution. Okay, and we start from the acid form of this one. Okay, hypochlorous acid is um, is a weak acid. Okay, it dissociates into proton and hypochlorite ion. And uh, for this one, we can write Henderson-Hasselbalch equation like this: pH equals pKa plus log and the ratio of hypochlorite and hypochlorous acid concentrations. Okay, and pKa is already known, 7.53, and this solution is already buffered at pH 6.20. Okay, so we can write this equation, and then this is very simple. We can write, we can solve for this ratio. Okay, and finally we get the ratio of these two ion species is 0.047. Okay, yeah. Important implication here is that we do not need to know how much sodium hypochlorite was added or the total volume. Yeah, we don't need to know, yeah, these quantities. Okay, look at that. Simply we need to know the ratio of these two species. All right, and it is not important how much sodium hypochlorite you have. Okay, that's not important. Also, not important is the total solution volume. Okay, but what's the difference? Although we uh, we know this ratio, and then we get this pH. Okay, but what if? What makes the difference when we have more hypochlorite and when we have less amount of sodium hypochlorite? What makes the difference? Okay, so you understand my question? Okay, so actually, yeah, the pH itself, to maintain this pH, the the amount of sodium hypochlorite may not be important, but they make some difference. Okay, and then here, I'm sorry, more, more amount of sodium hypochlorite makes, buffer. You'll see later, makes the buffer, the capacity very high. Okay, so if you use small amount of this species, then your buffer capacity may be very low. In other words, you make only, not a good buffer, right? So to make a good buffer, you need to have more amount of, each species. Yeah? That's the answer. You understand, right? Here to make this ratio, yeah, you can have, this concentration about 0.0467 and this species 1, yeah, to make this one. Or if you have the concentration of hypochlorite 0.47, and then to make this ratio constant, this hypochlorous acid concentration need to be 10 times larger, eh? And then the buffer capacity increases. Okay, you'll see soon, right? Okay, let's keep going. This example shows you how buffer is in action. Okay, yeah. The example is that this one. This is a tris buffer. Okay. This rather complex compound. The full name is tris hydroxymethoxy. Okay. Tris means three. Okay. Hydroxymethoxy aminomethane. Okay. The basic structure is the methane. Okay. And this is a basic form, and in the fully protonated form is this one. Proton is goes to this nitrogen atom. This is a fully protonated form. This is maybe we say BH plus form. Okay, it undergoes dissociation to produce this P form and proton. Okay, the question is there are two questions. Find the pH of a solution prepared by dissolving 12.43 gram of tris. This one, whose formula weight mass is this one, 121.135, and plus 4.67 gram of tris HCl. Okay, this one usually it is you can buy this form, but it is HCl salt. Okay, the formula weight mass is larger than this one. Okay, 157.596 in 1 liter, yeah, for the simple calculation. Find pH. Okay, well, this one pKa for this one is already known here. Okay, pKa is let me see, okay, yeah, here 8.075. Okay, to apply this Henderson-Hasselbalch equation, you have to know the concentration. Okay, concentration of this form and this form. Okay, but here, since they are all dissolved in the same solution, so solution volume doesn't matter actually. Okay, so you don't have to worry about the solution volume. Okay, you only calculate the moles of each compound. Okay, let's calculate first. This P form. Since the P form, the mass is this one, and then you divide this number by the formula mass, and then you get this number. Okay, 0.1026 mole. Yeah, if we divide by the solution volume 1, this is molarity. Okay, but actually, you don't need to worry about the volume. Likewise, you calculate the moles of pH plus form. Okay, you added this amount of pH plus and then divide by this formula mass. Okay, and then you get this one and apply this one, this and this Hasselbalch equation. And then you got 8.61. All right, here is a note. Okay, the volume of solution is irrelevant. Okay, because volume cancels in the numerator and denominator in logarithm right here. Because those forms are in the same solution. Okay, yeah. Okay, and then second question is that now you added 12 milliliter of 1 molar HCl to the solution. Yeah, here. Okay, HCl is a really strong acid. Okay, and you add 12 milliliters. Okay, and then what happened? 12 milliliter of 1 molar solution, and then what is the moles of HCl? You simply multiply these two numbers, and then you get the number of moles of HCl. The protons is simply 0.012 mole. Okay, now this proton only reacts with the base form. Okay, originally is the mole of B is here 0.1026, and this is initial condition. You added this one, and then as a result, original moles of pH plus is this one 0.0296, and after reaction, this one is decreased by this amount of a proton. Okay, so final amount is 0.0906 for B, and pH plus amount increases by this amount, okay, to 0.0416. So here is the pH. pH equals, we apply the same Henderson-Hasselbalch equation. In this case, the moles of B and moles of pH plus are different, and using new numbers, we got 8.41. Okay, so after adding this amount of very concentrated strong acid, pH changes by only 0.2. Right? It decreases, okay, by 0.2 only. All right, this is amazing. Right? Although the strong acid was added, pH change is very little. Okay, so that's the power of Popper solution. Okay, now you appreciate how Popper is really in action. Okay. All right, and then second question is uh, to calculate how to prepare a Popper solution. Yeah, okay, let's read this question. How many milliliters of 0.5 molar sodium hydroxide should be added to 10 gram of tris hydrochloride to give a pH of 7.6 in a final volume of 250 milliliter? Okay, this one is rather complicated. Okay, at first, you know, it is formidable task. Okay, oh, you may say, oh, Professor, I cannot solve this one. Okay, but let's do it step by step. Okay, question is how many milliliters of the sodium hydroxide should be added to this one, tris hydrochloride. Okay, so we translate this sentence into equation. Okay, pH plus, yeah, this is a tris hydrochloride form, and you add a strong base, and then it completely reacts to B and plus, I'm sorry, here is a H2O. Okay, it doesn't make any difference. All right, so pH plus amount will be decreased by the amount of hydroxide, and B should be increased by this amount. But since initially there is no B, only pH plus, okay, the pH plus amount is, you divide the 10 gram divided by formula mass of tris hydrochloride. Okay, what's the and then it is no, this number you got, this number 0.0635. Okay, this number, and then when you added hydroxide, and then this one decreases by x amount. Okay, and our the goal is to calculate this x. Okay, and OH minus is completely, you see, consumed. As a result, you get B. Yeah, so initially there is no B, and then now B amount is x. Okay, and then apply this Henderson-Hasselbalch equation. Okay, your final pH, your target pH is 7.6 equals this one, pKa for tris hydrochloride, and plus, yeah, this one, yeah, this one goes to the denominator, this one goes to a numerator. Yeah, and then you solve for x. Okay, oh, I'm sorry, and x, yeah, you get 0.016 more. Okay, 16 more, and what's the question? How many milliliters of this one? Okay, yeah, so here is your amount more, and the concentration is 0.5 molar. Okay, so to calculate the volume, you have to divide this mole, number of moles, by concentration. Okay, and here 0.016 mole divided by 0.5 mole per liter, and then you get 0.032 liters. Okay, and 32 milliliters. All right, yeah, here final volume actually doesn't matter. Actually, it is not important. Yeah? Final volume is whether it's 200 milliliters or 500 milliliters or 100 milliliters, doesn't matter. Your pH calculation is not affected by the final volume. Okay, Wonderful. Here, let's read this sentence. Preparing a buffer in real life. What does that mean? Here is an example. To get 1 liter buffer of 0.1 molar Tris at pH 7.60. From this example, you may realize that to prepare the buffer solution which acts at certain pH value, you need only one component. Okay, in this case, tris hydrochloride. You don't need tris. Okay, only one component. And to prepare to adjust the pH, you need strong base or strong acid. Okay, if you start with tris, okay, the tris compound, to adjust the pH, you have to add strong acid HCl. Okay, yeah, and then you monitor the pH using a pH meter while you're adding, in this case, NaOH solution, and then the pH meter indicates pH of 7.6, and then you stop adding the NaOH solution. That's how it works. Why is this necessary? Because in many cases, you have only one component. Yeah? In this case, ordinarily, yeah, you are looking for tris hydrochloride and tris at the same time. But usually you have only one component, tris hydrochloride or tris, but NaOH or HCl. Yeah? Those the regions are very very common. Okay, you understand? Yeah, that's how we prepare in real life. Okay, yeah, and that's the very accurate way of preparing a buffer. Well, this demonstration, you see, demonstrate how buffer works. Okay, this is just illustration. As buffer is used up, it becomes less resistant to change in pH. Okay, let's consider this mixture. Yeah? By or hydrogen sulfite and sulfite ion. Yeah, the initial concentration is 10 to 1. This one is 10 times higher than this sulfite. And let's examine what will happen when you add this one formaldehyde to this mixture. Okay, anyway, the Henderson-Hasselbalch equation is given by this one. Okay, this one. Yeah, here is the the dissociation reaction. pH equals pKa, and the pKa for this hydrogen sulfite is 7.2. Okay, plus log and the ratio of these two species. Okay, initially it is, since the ratio is 10 to 1, and initially is 6.2. Okay, it start 6.2. All right. And then let's see what will happen when you add formaldehyde to this mixture. You see formaldehyde react with both species. Okay, first with bisulfite or hydrogen sulfite, and as a result you produce eventually this one, this rather unusual species. And also this formaldehyde react with sulfite. Okay, sulfite, and it gives what, which is species, this species. Okay, and then if you with these two reactions, maybe if you subtract, okay, subtract the first one, the second one from the first one. Okay, and then you get this net reaction. Okay, which is this one plus bisulfite, and becomes this species, and this one sulfite is regenerate. Okay, it is consumed here, but it's regenerated. Okay, so actually from this equation, you see by adding formaldehyde, this bisulfite keep consumed. Okay, this is keep being consumed, but this one sulfite concentration is constant, so it is keep consumed, okay, and then what, these ratio becomes more and more, is larger, okay, becomes larger and larger, okay, and then eventually when this one bisulfite is totally consumed, this you see this ratio is very, becomes very big, and pH, abruptly increases, okay. Now this is the result, and you start, here, but not exactly 6.2, but around 6, and then you watch pH change as a function of time. It slowly increases, okay, and then uh, at the end of this total consumption of this species, pH now rapidly, very rapidly increases to this value, okay. Here, this pH increases slowly. Why? Because this bisulfite is being consumed, and then after, almost you know consumed, and then pH suddenly increases. All right, yeah.